We want you to make a small function generator to observe some wave shapes and think about some circuits. And as part of the pre-lab, we would like you to design some component values. So this is from experiment 2 in the laboratory, but it's also your homework, if you like. And you won't be able to get into the lab to do the lab unless you've got a decent attempt at coming up with some numbers. The circuit in question actually is made up of 2 op-amp circuits. There's a resistor which is called R, and there's an op-amp here, and it's an integrator. We will eventually, if we haven't already, discuss integrators in EEE 225. But if you haven't seen them, it's okay. We'll discuss them a bit now. And also the material that I'm talking about is on the laboratory sheet as well. So you don't actually have to pay any attention to what I've got to say. You can just work through the sheet and you should come out with a good attempt. The other circuit that's involved is a Shilling Trigger, which is a circuit you might have seen if you've done some GCSE or A-level electronics, but you probably haven't come across here at Sheffield, so we tend not to discuss them very much, but they're relatively straightforward. It's an op-amp circuit, but in this case you can see the feedback is actually going towards the non-inverting input, not the inverting input. And these behave entirely differently to amplifiers. They're not amplifiers at all, even though the circuit shape looks a bit like one. Oh, I made a mistake. There should be an extra resistor in there, shouldn't there? There's a resistor in there. And I think it's a kiloohm. And then it comes up here. And Zener diode. And Zener diode. Of course, we talked about Zener diodes in 118. So they're entirely familiar, I'm sure. And these turn out to be 4.3 volt breakdown Zener diodes, both of them. Of course, if you were to forward bias one, it'd still turn on with 0.7 volts across it, but they break down in reverse at 4.3. So that's the circuit in question, and there is a specification as well. And the specification for the circuit says we'd like a frequency of a kilohertz, and we'd like a sine. No, not sine. Sine would be good, but it doesn't do sine. Square and triangle. And we'd like plus and minus 5 volts for both. And it turns out that the triangle comes out there, we call it VT, and or VOT I think perhaps we call it, but it doesn't matter. And this one is called, we'll call it VS for square. And your job is to find out the value of C, the value of R. I think this is called R1 and that's called R2, but it could be the other way around, it doesn't really matter. So now maybe you're feeling a bit lost because there's no input to this circuit. It doesn't have a signal going into it, it just makes the signal. Where would you start? You've got this sort of loop. You know there must be some feedback. There's feedback around here, there's feedback in here, there's feedback around the whole lot. Where should we begin? Well, we can begin a bit by talking about the integrator and Schmidt trigger. So I'll probably have to rub off a bit of this diagram. When we look at this circuit, we might be thinking, well, it looks like an amplifier. Actually, it's not an amplifier, and it doesn't have a virtual earth either. Quite important to bear that in mind, otherwise you might fall into some assumptions that you shouldn't. So what we must do is say, well, how does the feedback work here? Well, if I have a small voltage on the output that propagates back towards the input, and I make sure my op-amp still obeys AV, V plus minus V minus, which it does, all op-amps will obey it, irrespective of what's going on with feedback. Well, if this goes up, and that goes up as a result, this fraction will get bigger, which will make this bigger. So this will get bigger and it will get back to here and make that go up, which will make it even bigger, which will make that even bigger. And it very quickly, if there's any difference between V plus and V minus, the inverting and non-inverting and inverting inputs, the output will go up to whatever the plus rail is, which in this case is plus 15, or go down to the minus rail, which in this case is minus 15. There isn't any amplifier type bit in the middle. It'll fall to one or to the other. It's like trying to stand a pin up on a flat surface. It'll always fall. So the question you've got to ask yourself is, what do I have to do to V in to get it to change state? And you can ignore the 1K for a bit, we'll worry only about V out. Let's have a current that flows like that, and a current that flows like that. And we'll call this one I. And this is still very high impedance looking in here, so these two currents are going to be equal to each other. We'll say that, tell you what, just for clarity, we'll ditch the 1K for now and do it like that. This current VO, we'll call that VO. I know it's called VS up there, but let's call it VO. We'll have a current I is going to be V plus minus VO over R2. And let's imagine for the moment that this is actually below 0. And if that's going to be below 0, V in must be below 0 as well. If you don't like the way I've just come out with that, when you get to the end, if you go back through the analysis, you'll see that it must be true. Similarly, if I said this is going to be high, this must also be above 0, but you still can't see that until you've got to the end and then go back through it. But let's say V out is below 0, V in is below 0 as well. Well, these are potentially divided by R1 and R2. This is high impedance, so it doesn't take, it doesn't get involved. So this node here must be below 0. What do I have to do to make it change state? Well, I've got to make it so that V plus and V minus are just about equal, because then it will be on the point of toppling from one state into the other. Now V minus is 0. So my question, what do I have to do to make it change state, has changed into, what do I have to do to make V plus equal 0 equal V minus? Well, this current that flows in R2 is V plus minus V out over R2, and I also know that I is going to be V in over R1. I know that because I've just said that the situation I'm heading towards is where V plus and V minus are equal. And if this is 0, then that's going to be 0 as well. But it's not a virtual earth. It is not a virtual earth. If this was at plus 5, I'd be looking for a plus 5 situation here. It wouldn't be Earth at all. Don't get carried away with virtual Earth. It's definitely not virtual Earth. So I can stick these two equations together if I want to, and I can also sub in 0 for V plus, because I know it's 0. So I have V in over Ri is equal to 0, which comes from there, minus V out over R2. Bit of fiddling around, I'll end up with V in is equal to R1 V out over R2. The situation now is I can say, well, what do I need V out to be, and what do I need V in to be to make that V out happen? And then I can choose my resistor values. Or you can pick one and work out what the other has to be. We will come back to that in a bit, but we need to talk about the integrator first, and then we can bring the whole circuit together. Usually when we're looking at these sort of trigger circuits, we'll draw a graph, and the graph we'll draw has a V out axis and a V in axis, and everything to the right of the vertical is V in positive, and everything to the left of the vertical is V in negative. Everything above the horizontal is V in positive, everything below the horizontal, V out, sorry, V out below the horizontal is negative, V out above the horizontal positive. And what we'd say is, I'm going to start off either at very low V in or very high V in. I'm going to work my way towards the other side and see what happens to V out. So for this circuit, we've got V in very, very small, V out very, very small as well, because I just rubbed out the equation, but it was V in is V out times R1 over R2. So very, very, very small, get to 0, all of a sudden changes state. V out goes as high as it can, and for all values of V in higher than 0, V out stays high. And if I derived, well, it wasn't really a derivation, did some equations for this point down here, where V in was low and V out was low, but you could equally well do it from up there if you wanted to, and start off assuming that V out is high, and then working out that V in must be high as well, and then doing the calculation. So anyway, you might see it like this. Sometimes these circuits have hysteresis, where if I was wobbling about the 0, it could be changing state pretty frequently, and that might not be desirable in certain situations. So sometimes you can adjust using some extra circuitry so that it will, if you're going that way, it will come down there, but if you're going this way, it will go up there, and if it's in this bit in the middle, it won't change state from whatever state it's in now, even if it looks like it's the wrong state. But there's no hysteresis in here. If you want to read about these circuits a bit more, you'll find them in Horrocks and Hill, 3rd edition, and you'll find them in Microelectronics by Sedler and Smith, and you'll find them in Microelectronics by Millman and Grable. Let's talk about the integrator for a bit. I get rid of my green box. No, it's not really a box, it's a circle. Get rid of that, and the rest of the specification can go for a bit. I've got here a situation in which I'm going to inject a current. I'm going to inject a current by putting voltage on this point here. This is essentially an amplifier with frequency dependent feedback. So at very low frequencies there's very, very little feedback. At DC there isn't any. As frequency goes up, feedback becomes a greater factor of the output. So let's imagine I inject a current. Current goes in like that. Well, there can't be any current going in there because the usual rules apply. So there must be a current here to equal this, the current flowing through R. If that's the case, a current in a capacitor, or current flowing into or out of a capacitor, must give rise to some change in voltage across that capacitor. So I could put in maybe a VC like this. And if I asked you for an equation, you'd probably say that I is equal to C dV by dt. And if I said, or another equation, you might say, oh, well, in that case, V is equal to 1 upon C integral I dt plus a constant that I should call K, because I've already got C here. Interestingly, if you want to know what K is, if I said to you, deal with this circuit, will you? By the way, it's been switched on for a long time and the capacitor's charged up to 3 volts. That's where your K would come in. As it is, we can assume that this doesn't play any part, but we mustn't forget that it's there. So, the voltage across this capacitor is proportional to the time integral of the current which I pass through R, hence integrator. So what should we do with it? Well, we're trying to make something that generates a signal. Our signal is going to look a bit like this. We'll have some period where it's low and a period where it's high, period where it's low, period where it's high. And this is going to be +5, it says so in the spec, and this is going to be -5, also says so in the spec. And it also says in the spec that the period has to be able to give us a kilohertz. So a kilohertz in period terms is a millisecond. And we can say that the duty, I think it says in the spec, is 50%. So I know that half of the time it will be high and the other half it will be low, and the time that it's high and low for is 500 microseconds. That's a mu. Fine. So I know that to make this -5 to +5, I've got to get it so that this point here is just the right voltage to switch that bigger than that to make that go up. And that going up will pass a current through R, which will charge up this C, which will cause a voltage drop across the C that will force this downwards. And when this hits the this gets to the voltage that makes that slightly smaller than that, this will flip state, that will go down, the current will pass through R the other direction and discharge this capacitor, and the voltage across the capacitor will get smaller, this point will rise, this point's at 0, remember, so that's why that goes up and that gets smaller. And we'll be working our way back towards the point where this just gets bigger than that, that will change state and go up, and down we go again. Don't worry if you didn't follow that, you've got to sit down and think about it. It doesn't really matter where you start your analysis either, because you're in a loop. You can start it with your integrator or you can start it with the trigger. So this is the point where this has just gone high because that's just a bit bigger than that. This has just gone high, so R is passing a current in the direction I've shown, and that's causing a current to leave the capacitor. In fact, the arrow should be the other way. Like that. And that represents, that gets bigger, the capacitance gets bigger, that drops. So I have to actually stand here and work it out. It's not a case of remembering it, it's a case of reasoning it out. Now that should give rise to, so how on earth do I come to this? This is VT is in green. VT is in green and VT is dropping like that because I'm integrating this square. And if you integrate the square, you'll get a ramp. And if you differentiate the ramp, you'll get a constant rate of change, which will give you the square. If you're not happy with these things, then they are in various textbooks, and it'll be a good idea to get familiar with them. You will be becoming familiar with them anyway, because you'll find them in communication electronics or signals and systems and so forth. So in the period just after that, this has now got to the point where that's slightly smaller than that because this has been dropping, because this has been changing its voltage. This gets smaller than that, that flips down, and the current now leaves that and charges or discharges that depending on the point of view. As a consequence, its voltage does that. And then back here, well, we're in this state again, so that should look like that. Well, possibly a bit more like that. I think there's a bit missing off the front of my graph. So what about VOS, VOT? So green is VOT. What about VOS? Well, VOS is already there, it's in black. I know VOS is going to look like, because my trigger is going to either be output is higher, output is lower. Because you may say, if you're on the board, hang on a minute James, didn't you say there were plus and minus 15 volt supplies? I did. That's where this resistor that we removed earlier comes into play. Let's put it back. The other thing that I took away earlier were the xenodiodes, and they're also involved. By the way, I'm not going to tell you how to get the resistor values or the capacitor value. I'm just going to explain how the circuit works, and you have to figure out the values yourselves. We had some xenodiodes here. And I said, well, V out's going to go up to plus 15 and minus 15, but this voltage here could do something else. In my calculations, if I said that V in and V out had to be the same, you will know pretty quickly that R1 and R2 are going to be equal because of that equation that I had down here a while ago. The one involving R1 and R2 and V out and VO. You can rewind if you want. So let's say this is going to get to plus or minus 5 volts. And this is going to get to plus or minus 15. Well, let's say this is plus 15 and that's plus 5, because that's the situation that we could end up in, one of them. That would leave us with 10 volts across that 1K. That's alright. How do I end up with plus 5? Well, this is a 4.3 volt Zener diode, and this is a 4.3 volt Zener diode. So they'll break down at 4.3 volts. Now, if this is plus 5, and this is the ground, this Zener diode here will be reverse biased. This cathode is more positive than its anode, so we'll end up with 4.3 volts. This one, on the other hand, well, it's going to be forward biased because its anode is at higher potential than its cathode, so we can expect 0.7. And if you were to add up 0.7 and 4.3, you'll find that up to 5. So that's how we end up with the 5 volts. Of course, 10 volts, 1 kilo ohm, current, 10 milliamps. Ohm's law on the resistor. 10 milliamps here. Okay. Now that 10 milliamps has to service several things. It has to provide enough current here to make our Schmitt trigger go. It has to provide enough current down here to break this Zener diode down and to forward bias that one, or in the other half cycle where this is minus 5, it has to forward bias that one and break that one down. And it has to supply a little current that goes back through R to charge up and discharge C appropriately to give us a nice triangle and to change the state of the Schmitt trigger and to make it all go. So you can't just choose some currents at random. They've all got to go up to 10. You don't really know what this current's going to be through the Zener diodes. This is the one that's the rest. So you choose your current that goes through R2 and by extension through R1, because they end up equaling when it flips, when the state of the Schmitt trigger flips. And you can choose your current that goes through your R to charge up your C. You can't choose this current, but it is all of the rest. So deal with your C and your R, maybe then deal with your R2 and your R1, or possibly the other way around if you prefer. Everything else here. Just got to make sure that this one plus this one isn't more than 10. In fact, if it's more than about 7, I'd be a bit worried. Milliamps, I mean. So what about the value of C and R? Well, you've got several things available to you. When I was over here, I wrote an integral equation for the capacitor, but I also wrote the differential equation for the capacitor, and that's the one that I find most useful in this situation, although you may find it differently. I was C dV by dt. Well, actually I can say what my I is going to be, if I want to, by picking a value of R. That might not be a good idea though, because there are fewer values of C available in the lab than there are values of R. So you might want to pick C and work out what R's got to be. But two things you definitely have are a dt and a dV. You know what your dV is. We're going to do it in blue because we've already used green. Your dV is that much, which is 10 volts. And your dt is the amount of time it takes you to shuffle those 10 volts off your capacitor, or from across your capacitor rather. And you've only got 500 microseconds to do it in. And then half a cycle later you have 500 microseconds to shift 10 volts again. Happens to be the other way, but that's neither here nor there. Circuit certainly doesn't care. So you've got a dV, 10, and you've got a dt, 500 micro. You can choose your C if you want, and that allows you to calculate an I. Now, you know this must be 0 because there's a virtual earth here, because this amplifier with frequency dependent feedback, still an amplifier. If that's 0 and you know this is either plus or minus 5 and you've got a value for I, you will know the voltage across R, 0, 5, 0, minus 5. You've got everything, you just smoosh it together and come up with some numbers. In day 2 of the amplifier lab, you'll be using the two op amps here to make an amplifier, to do some experiments to do with gain bandwidth products and that sort of thing, and also to make a self-starting oscillator, which is an electronic system that produces a signal. It doesn't require any signal to make it go. It has DC only input and it oscillates by itself. This op amp and this op amp are the same, but this one has some extra bits that we've put on the board. Key amongst them is this potentiometer here, which you can turn. In fact, you can turn it forever, so don't get carried away. Actually, it only has about 270 degrees worth of turn, and that gives you the full range of values that are available, which just so happens to be 0 to 100 kiloohms, but you don't need to worry about that too much. So even if you keep turning, all that happens is it goes round again. The reason that we have this is we can adjust the 0 output of this operation amplifier. Now, if you've been in my lectures, or maybe we haven't had them yet, it depends exactly when you do the lab, but you will at some point have heard that an op amp with negative feedback wants to keep V plus and V minus equal to each other. And if it can manage that, it might have, and there's no inputs, its output will be 0. Actually, inside the op amp there are many transistors, and they're not all identical. If they were, then what we say usually about the op amp keeping V plus and V minus together and the output being 0 if the input's 0 could be true. But things are never as simple as we make them out to be. Part of an engineer's job is to use simplifications and mathematics and rules about how the world works to try and design things that are of use to people and make their lives easier and so on and so forth. To make the math tractable, we have to make lots of simplifications, and actually this is one of them. Even if V plus and V minus are at the same potential, the output will not be quite 0. And we can adjust some bits inside the op amp by turning this knob, which will allow us to tune around the 0 point, probably only about 20 millivolts above the 0 to 20 millivolts below the 0. And there is a point in the lab in day 2 where, to get the waveforms that we expect you to see, the sort of textbook type waveforms, you will have to turn this to get 0 here while you're measuring it with an oscilloscope. So when it says use the top op amp, there is a good reason, and if you use the bottom op amp, you won't be able to tune it to see what we expect you to see.